Today, I will briefly review the paper, Dense Passage Retrieval for Open Domain Question Answering. Open domain question answering refers to the task that asks a model to produce answers to factoid questions in natural language with the lack of the relevant context for any arbitrary asked factual question. To solve open domain question answering task effectively, a simple framework called Retriever-Reader Pipeline is widely used. Retriever-Reader Pipeline consists of two stages. First, a retriever selects a small subset of passages that is related to the query from the vector database, where some of them contain the answer to the question. Next, a reader can thoroughly examine the retrieved context and identify the correct answer. This paper mainly focuses on how to train a good retriever with limited amount of data. Before getting the paper, let me explain the basic components of a retriever briefly. Retriever consists of two types of encoders, which are a query encoder and a passage encoder. To find relevant passage to the given query, it uses maximum inner product search with dot product of their vectors. When training a retriever, we need a relevant passage and several irrelevant passages for a given query. From the above equation, you can see that each data instance contains one question paired with one relevant passage along with n irrelevant passages. The goal is to create a vector space such that relevant pairs of questions and passages will have smaller distance than the irrelevant ones by optimizing the given loss function. Challenge for learning a good dense vector representation is that in contrast to positive examples, which are often available explicitly, negative examples need to be selected from an extremely large pool of data. How to select negative passages is often overlooked, but could be decisive for learning a high-quality encoder. In the DPR paper, various training schemes are discussed, but I will focus on the negative sampling. This paper suggests three methods. First, random means you choose any random passage from the corpus. Next, BM25 means that you choose top passages returned by BM25 which don't contain the answer but match most question tokens. You can see this method as choosing hard negatives. Finally, gold means that you choose positive passages paired with other questions which appear in the training set. This table shows the experimental results of different training schemes. Number n refers to the number of negative examples, IB refers to the usage of in-batch training, and top K columns refers to the top K retrieval accuracy on the given question answering dataset, which is called natural questions. Let's look at the very first block of the table. All three different methods use 7 negative examples, and in-batch negative training is not used. You can see that the top 5 accuracy is highest for BM25 method, which uses hard negatives. However, when looking at top 20 and top 100 accuracy, hard negatives actually does not have any effect and even worsen the performance. This implies that when K becomes bigger, using randomly chosen negatives can be an effective solution rather than only using hard negatives. Next, in order to understand the transition from the first block to the second block, you should understand the concept of in-batch negatives. Assume that we have big questions in a mini-batch and each one is associated with a single relevant passage. Q1 and P1, Q2 and P2 for example in this figure. Let Q's and P's are question and passage embeddings. Then for all queries and passages, you can make B by B matrix of similarity scores where each row corresponds to a question paired with B passages. In this way, we can reuse computation and effectively train on B-squared question passage pairs in each batch. In this figure, green boxes indicates the similarity score of positive pairs, whether red boxes indicates similarity scores of negative pairs. This method is not only computationally efficient, but also achieves great performance. You can see from the table that in-batch negative training improves the results substantially. The reason for this is that in-batch negatives can produce more negative pairs for individual passage in a single batch, since same passages are reused in a batch. This is quite different from the base method, which has only one negative pair for individual passage in a batch. The second block shows that more negatives lead to greater performance. This is because more negatives produce more query document pairs and therefore increases the number of total training examples. The transition from the second block to the third block shows in-batch negative training with additional hard negative passages that have high BM25 scores given the question. This figure shows the process. The first B columns indicate in-batch negatives with original GORT negatives, and next B columns are additional BM25 hard negatives. Here, passage P1' is the hard negative passage for the query Q1, and P2' is the hard negative for Q2, and so on. These additional hard negatives lead to substantial performance improvement, even though the total number of negatives is about half compared to only trained with gold passages. This is quite interesting considering that there wasn't much performance improvement when only BM25 was used in the first block. The third block shows that adding a single BM25 negative passage for each query improves the results substantially, while adding two hard negatives does not help further. In conclusion, how to select negative passages is crucial for training a good dense retriever, and this paper showed several alternatives of choosing those negative passages.